Welcome to The Explainer. Today, we are cracking the code on logic puzzles. You know the ones. They pop up in competitive exams, job interviews, or just for fun, and they're really designed to see how you think under pressure. So, we're not just going to solve a few puzzles today. Nope. We're going to pull back the curtain on how they work so you can build a rock-solid strategy for any logic problem that gets thrown your way.
We've all been there, right? You're staring at the page, the clock is ticking, and a problem that looked kinda simple a minute ago suddenly feels like this impossible mountain to climb. Well, that pressure is exactly what exams use to test how you reason. So let's turn that feeling around and replace it with a clear, step-by-step approach.
All right, let's dive right in with a classic ranking puzzle. This is a perfect way to get our logic circuits warmed up and see a really fundamental problem-solving technique in action.
Okay, here's our first challenge. Now, it looks pretty straightforward, but it's really two mini problems rolled into one. Your first instinct might be to just add all those numbers together, but hold on. The key here is to figure out the total number of boys in Javon's row first, then do the exact same thing for Vikas' row. Only then can we add them together.
And for this type of problem, this little formula is your best friend. But you might be asking, why do we subtract 1? Well, think about it. If you count from the front to find a person, and then count from the back to find that same person, you've actually counted them twice. That -1 is the secret sauce. It fixes the double count and gives you the real total.
So first up, let's use the formula for Jivan's row. He's 7th from the front, 11th from the back. So we add 7 and 11, which gets us 18. Then we do that crucial subtraction of 1 to account for Jivan himself, and boom, that tells us there are exactly 17 boys in his row.
And now we just rinse and repeat for Vikas. He's 10th from the front, 12th from the back. You add those up, you get 22, subtract 1, and you've got 21 boys in his line. See? It's a simple, methodical process that just works.
So here's the beautiful part. Once we broke the problem down into smaller, easy-to-solve pieces, the final step is a piece of cake. We just add the 17 boys from Jivan's row to the 21 from Vikas' row, and we get our final answer, 38.
Okay, warm-up's over. Now it's time for the main event. A really classic, multi-layered problem about a painted cube that gets cut into a bunch of smaller pieces. This one is going to seriously test your spatial reasoning.
So let's set the scene. Picture a big 10-centimeter cube. The top and bottom faces are painted red, the front and back faces are painted blue, and the left and right faces are painted black. Then, this whole thing gets sliced up into little 2-centimeter cubes. Really getting this initial setup in your head is absolutely the first step to figuring out everything else.
Now, before we can solve anything, we need to find one super important value. We're going to call it n. N is just the number of small cubes you can line up along one edge of the big cube. And to find it, we just divide the side of the large cube, 10 centimeters, by the side of a small cube, which is 2 centimeters. So that gives us an n of 5. Remember that number. Seriously, it is the key that unlocks this entire puzzle.
Now that we have n, finding the total number of small cubes is easy peasy. It's just like finding the volume of a cube, right? Length times width times height. Here, it's n times n times n, or n cubed. So 5 times 5 times 5 gives us a grand total of 125 little cubes.
So to tackle the questions that are about to come our way, we need a toolkit. Instead of trying to think about 125 different cubes, we're going to be smart and categorize them. Let's break down the anatomy of this cube and figure out the different types of smaller cubes we're actually dealing with.
This table right here is our roadmap. It basically shows that any one of those 125 small cubes has to be one of just a few types. It could be a corner piece, which gets 3 of its faces painted. It could be an edge piece with 2 painted faces. Or it could be a face piece right in the middle with only 1 painted face. But hang on a second. What about the cubes with no painted faces?
So, what is that mysterious fourth type? Well, we've got a great analogy for this. Chili paneer. You know how the outside is covered in that delicious spicy coating, but when you bite into it, the paneer on the inside is totally untouched? Our cube is the exact same way. The paint is only on the surface, which means there's a core of smaller cubes deep in the center that have 0 painted faces.
And wouldn't you know it, there's a simple, beautiful formula for finding these hidden inner cubes. It's n-2 cubed. Now the -2 is because we're basically removing the outer layer from both sides of the cube. Since our n is 5, that's 5 minus 2, which is 3. And 3 cubed is 27. So deep inside that painted block, there are 27 completely unpainted cubes.
All right, our toolkit is ready to go. We know all the different types of cubes and we've got our formulas. So let's jump into the first set of challenges and see how we can use this system to answer questions super quickly and with total confidence.
Okay, so we're going to solve for the number of cubes with 3, 2, and 1 painted face. Now that we have our logic all set up, these questions become simple calculations instead of some big, complex spatial puzzle. Let's start with an easy one. How many cubes have 3 painted faces? Just think about the cube for a second. Which pieces could possibly be painted on 3 sides? Only the corners, right? And any cube, big or small, has exactly 8 corners. So for any puzzle like this, the answer for 3 painted faces is always 8. No formula needed. Done. Next up, cubes with exactly 2 painted faces. These are the pieces that are sitting on the edges of the cube, but they're not the corners. The formula is 12 times n minus 2. So why does that work? Well, a cube has 12 edges, and that n minus 2 part tells us how many of the little cubes on each edge have 2 painted faces. Since our n is 5, that's 12 times 3, which gives us 36.
And that brings us to the last main formula in our toolkit. For cubes with only 1 face painted, we're looking at the pieces in the very center of each of the cube's 6 faces. So the formula is 6 times n minus 2 squared. The 6 is for the 6 faces, and the n minus 2 squared tells us the area of that central block on each face. For us, that's 6 times 3 squared, which is 6 times 9, which equals 54.
Okay, on to the final round. And this is where the puzzles get really clever. We have all our formulas, but now we have to apply our logic to questions where the exact wording is absolutely critical. This is what separates the good puzzle solvers from the great ones. Okay, I want you to look really closely at these 2 questions. At first glance, they look almost the same, but there is a huge difference. Question A is super specific. It demands exactly 2 painted faces, 1 red and 1 black, and it insists that all other faces are unpainted. Question B is a bit more relaxed. It asks for 1 blue and 1 red face, but it says nothing about the other faces. That silence is the key.
So let's break down question B. Because it doesn't say and no other faces painted, we're looking for any cube that has at least 1 blue and 1 red face. So we start with the edge pieces that are only red and blue, and there are 12 of those. But we're not finished. What about the corner pieces? The 8 corners are painted red, blue, and black. So do they have 1 blue face and 1 red face? Yes, they absolutely do, so we have to include them. That means we take our 12 edge pieces and add all 8 corner pieces, giving us a total of 20.
So, what's the big takeaway from all this? Well, formulas and shortcuts are awesome for speed, but they can fail you in the trickiest problems if you don't know why they work. What will never fail you is understanding the core logic, knowing why a corner piece has 3 painted sides, or why we subtract 2 from n. That's the real power that lets you break down and conquer any puzzle you face. So the real question isn't just, can you find the answer? It's, are you practicing the logic?